Okay, good morning all. So we were dealing with weighted residual methods in the previous class. And in this class, we are going to look at one of the weighted residual methods, and that is Galerkins method. It is most popular method in all the weighted residual methods for the obvious reason that it gives you accuracy better than other methods. Instead of solving the same problem that we were solving earlier, now let us solve a problem in civil engineering domain. Let us say you have a cantilever beam AB loaded with UDL of intensity 10 kilonewton per meter as shown, and a point load of 10 kilonewton at the free end as shown. Let us say end A is the origin, X is horizontal, Y is vertical. So deformation of this beam at each and every point in Y direction will be denoted by V of X, because we have standard notations now in FEM. U, V, W are deformations in X, Y and Z direction respectively. So in Z direction, this beam is going to deform, and that deformation we are going to denote it as V of X. So V of X will go on changing as I change X from 0 to 3 meters. Now you all are aware that governing differential equation for this beam is a second order homogeneous linear differential equation. EI d square V by dx square is equal to bending moment at X. So let us try to write down bending moment at X in this beam. So X is taken from left end. So therefore this distance, remaining distance, this one will be 3 minus X. And in cantilever beam, we always write down bending moment from the free end side so that we need not calculate the reactions. So therefore we are taking section at X and we are going to write down bending moment at X. So what will be bending moment? It will be 10 into this 3 minus X, and it will be hogging in nature because this is hogging. So on right hand side of the section, you will see that this 10 kilonewton is going to cause a clockwise moment, that is nothing but hogging, and by sign convention we give a negative sign to hogging bending moment. So M at X will have first component as minus 10 into 3 minus X. This minus sign is for hogging, and then due to UDL, the bending moment at this location is going to be 10 into 3 minus X bracket square by 2 hogging, and therefore negative sign. So bending moment at X is given as minus 10 into 3 minus X minus this 10 by 2 becomes 5 into 3 minus X square. So governing differential equation for this beam is EI d square V upon dx square is equal to minus 10 into 3 minus X minus 5 into 3 minus X square. Let me draw the figure of V of X so you will understand what I mean to say. So this is V of X. So at distance X from left end, this distance, this one we call it as V at X. So V at X goes on changing as X changes, and its double derivative with reference to X square into EI will be equal to bending moment, and that is given by this. Any differential equation is not complete if we do not specify the required number of boundary conditions, because unless there are required number of boundary conditions, we cannot solve that differential equation. So what are the boundary conditions here? Nobody is going to give you all the boundary conditions in the problem itself. For example, in this particular case, you will have to write down boundary conditions on your own. So what are the boundary conditions? So as support A is fixed support, therefore at fixed support, Y directional deformation is 0 and slope, that is rotation, is also 0. But what is rotation? Rotation is nothing but derivative of Y directional deformation with reference to X. So we used to say dy by dx is the slope, but now y here will be replaced by v because our notation for y directional deformation is v. So therefore dv by dx is going to be the slope. So what are the boundary conditions? There are two boundary conditions. At x equal to 0, v is equal to 0, and at x equal to 0, dv by dx has to be also equal to 0. Slope and deflection at this point fixed end are ought to be 0. So we have been given now two boundary conditions for a second order linear ordinary homogeneous differential non-homogeneous differential equation, and I'm sorry, homogeneous differential equation, and then we can solve this We have to solve this equation to get variation of v of x as a function of x. Now in weighted residual method, now may it be Galerkins method, may it be point collocation method, may it be subdomain collocation method. The first step in weighted residual methods is to choose trial functions. Trial functions are used to approximate the solution of a differential equation. So I'm going to choose trial functions, three trial functions, phi1 of x, phi2 of x, and phi3 of x. What is the requirement on these trial functions? These trial functions need to be admissible. That means they must satisfy these boundary conditions, and trial functions must be linearly independent. None of the trial function can be expressed as linear combination of other trial functions. Satisfying both these conditions, let me choose phi1 of x as x raised to 4. So you will understand what is phi1 of x dash. So first derivative of phi1 with reference to x, it becomes x cubed. So at x equal to 0, phi1 of x is 0 as well as phi dash of x is also 0. Therefore, both the boundary conditions are satisfied. Therefore, it is admissible trial function. What about phi2 of x? I have chosen phi2 of x as x raised to 3. So what is phi2 of x derivative with reference to x? So that turns out to be x square. If this is the derivative, I'm sorry, it is 3x square and it is 4x cube. Yeah, so phi2 of x dash is 3x square. Even at x equal to 0, phi2 of x is 0 and phi2 dash of x is 0. Therefore, this is also admissible trial function. Now let us look at phi3 of x. It is x square. Its derivative will be 2x. So phi3 of x dash, this is going to be 2x. Phi3 of x dash, that is going to be 2x. So at x equal to 0, phi3 of x is 0 as well as phi3 dash of x is 0. So therefore, this is also an admissible trial function. Once this is done, what do we do next? The next thing that we do is we express the approximate solution to this governing differential equation. That approximate solution, let me call it as u of x. So though we use u for x directional deformation, let us make an exception here. We say that u of x is approximately equal to v of x. So u of x is the approximation to v of x, and u of x can be written as linear combination of these trial functions. So I'm going to say it is a phi1 of x into a plus b phi2 of x plus c phi3 of x. So once we write down u of x approximation to v of x in this way, we substitute this in this governing differential equation. But before that, what we do is we take all the terms on one side. So what is the governing differential equation? ei d square v by dx square plus 10 into 3 minus x, 10 into 3 minus x plus 5 into 3 minus x square, 5 into 3 minus x bracket, the whole bracket square. This is equal to 0. So if we substitute exact solution, this equation is governing differential equation is going to be satisfied. But the moment I replace v by its approximation u, then ei d square u by dx square plus 10 into 3 minus x plus 5 into 3 minus x bracket square. This no longer remains 0 because u is the approximate solution. So whatever is the remainder, which is function of x, this is function of x, but we call that as residue. And we denote it by r, which is a function of x. So r is a function of x. So what is residue? Residue as a function of x now can be written as. So to write this, I will have to first differentiate u of x twice. So let me differentiate u of x twice. So u of x is this. So what is u dash of x? U dash of x is nothing but du by dx. And what is its value? So it is going to be a into phi 1 dash of x. But what is phi 1 dash of x? It is 4x cube. So it is going to be 4x cube a plus b into phi 2 dash of x. But what is phi 2 dash of x? It is 3x square. So it is going to be 3x square b. And the third term will be c into phi 3 dash of x. But what is phi 3 dash of x? Phi 3 dash of x is 2x. So I can write it as plus 2x into b, 2x into c. This is du by dx. Now let us try to find out the value of d square u by dx square. So d square u by dx square. This turns out to be 3x square it will be. So 4 into 3 it will become 12. So 12x square a plus 6x b plus 2c. I am just differentiating this equation. So d square u by dx square is this. Let us now substitute this in the governing differential equation here. So I will get the value, I will get the residue. So what is residue? Residue is ei multiplied by d square u by dx square. So that is nothing but 12a x square plus 6xb plus 2c. This is the residue. And in that I will have to add these two terms. So let me copy these two terms down. These two terms copied here. This is the residue. Now, in weighted residual methods, the next step that we do is we say that we need to minimize the residue in some sense. So what we do is summation. So in weighted residual method, we claim that integration from minus infinity to infinity weighing function into residue dx is equal to 0. Now just look at this domain, limits of integration minus infinity to plus infinity. Here we are interested in getting the solution of this differential equation only in the domain x equal to 0 to 3. So what is our domain? That also we need to write down here. X belongs to closed interval 0 to 3. If that is the case, instead of integrating this within minus infinity to infinity, I am going to integrate it from 0 to 3, and I'm going to say wi of x into r of x is equal to this is equal to 0. So wi of x is the weighing function, r of x is the residue. This I'm going to have three weighing functions because we have three unknowns here, because we have chosen three trial functions. So therefore, I will have to choose three weighing functions: w1 of x, w2 of x, and w3 of x. So these three weighing functions. Now, the choice of weighing function decides which weighted residual are we using. For example, if we use direct delta functions as weighing functions, we end up in point collocation method. If we choose step functions, Hillside step functions as weighing functions, we have seen that we end up in subdomain collocation method. In Galerkins method, we choose the trial function itself as a weighing function. For example, when I will take w1 of x as phi1 of x. So what is w1 of x? It becomes x raised to 4. I will take w2 of x as phi2 of x. So it becomes x cubed, and I will take w3 of x as phi 3 of x, that becomes x square. So I choose the same trial functions as weighing functions, and it leads to a Galerkin method, or Galerkin method of which is in the family of weighted residual methods. So having said this, now we have three equations. What are the three equations that are available with us? Equation number one, let us write down those equations. Equation number one, integration 0 to 3 w1 of x into r of x. R of x is this. So integration 0 to 3 x raised to 4 into ei into 12ax square plus 6bx plus 2c bracket complete plus 10 minus 10 into bracket 3 minus x plus 5 into bracket 3 minus x bracket square dx. This is ought to be equal to 0. This is our equation number one. What is equation number two? Instead of phi 1 of x, now weighing function becomes phi 2 of x. So I am just simply going to replace this x raised to 4 by phi 2 of x, and which is equal to x cube. So let me write down that. So I'm going to write down x cube here. This is our second equation. What is our third equation? So third equation now becomes this x3 needs to be replaced by third weighing function, which is phi 1 of x, and which is nothing but x square. So these many equations I have. Now what I'm going to do is I'm going to collect all the constant terms and all the coefficients of a, b, c in all these three equations. So let us do that. So what do I get? If I collect the coefficient of a in first equation, it is going to be 12 ei into x raised to 6. So I will have to integrate. So I will write down that here, 12 ei into x raised to 6. Integration of that x raised to 6 needs to be from 0 to 3 dx. This is the coefficient of a. Now let us collect the coefficient of b. You need bit of patience here, because the problem is mathematical in nature. There is nothing great about it, but you need a patience. Now, so let us collect the coefficient of b. So it is going to be 6x into this x raised to 4. So 6x raised to 5, and its integration from 0 to 3. And of course, ei is sitting there. So 6 ei integration x raised to 5 dx 0 to 3. This is the coefficient of v in first equation. What is the coefficient of c in first equation? So if you look at this, it is x square into ei into 2c. So 2ei and integration of x square from 0 to 3. So I will write down now the coefficient of c here. So plus 2ei integration 0 to 3 x raised to 4 dx c. And what is the constant term? Constant term is a term that does not involve a, b, and c. So the constant term is this next term. It will go on the other side and it will become negative. So, and it is multiplied by x raised to 4. So constant term is going to be equal to, this is going to be equal to equal to minus sign because it goes on the right hand side and becomes minus. Then you have integration 0 to 3. Then you have x4 sitting as it is here. So let me write down that x4 here. And then you have the terms within the bracket 10 into 3 minus x, 10 into 3 minus x, plus 5 into 3 minus x square, plus 5 into 3 minus x square dx. So now you look at this expression, you will understand that uh, this is going to be some number. EI is anyway going to be constant. So EI is going to always remain in our formulation. So therefore, it is some constant. This integration is some constant multiplied by EI into A. This integration is some constant multiplied by EI into B. And this integration is some constant multiplied by EI into B, is equal to right hand side is a definite integral of this quantity, this product, so it is going to be a constant. So similarly, if I simplify, collect the terms of a, b, c and constant, I am going to get another two equations in a and b, and then I can solve another two equations in a, b and c. I can solve for this, solve for these equations. I will get the value of a, b and c. I can substitute that in the expression for approximate solution, that is u of x here. So once I get the values of a, b and c, I have got the approximate solution. So this is how the Galerkin method works. Now I encourage you to complete this solution, find out the exact solution of this differential equation and plot these approximate and exact solutions over one another, the way we have done for other weighted residual methods. So there are total 3 points that we have learned here. One, always you may not be given a direct differential equation. You may be given a problem in physics, which you will have to translate it into a differential equation with governing boundary conditions. That was point number 1. Point number 2, the weighted residual formulation till the point where you write residue is same for all weighted residual methods. And point number 3, if you choose the trial functions themselves as weighing functions, the weighted residual method that results is called as Galerkins method. And Galerkins method is going to be the most accurate method and hence most popular method. So with this remark, let us stop today's interaction. I encourage you to solve this problem on your own completely as a practice. Thank you.